Hola, buenas tardes a todos. Creo que ya los profesores sí conocen a Jairo, los estudiantes ya son nuevos todos. Jairo hizo aquí su doctorado. Creo que había hecho la licenciatura en Cali. Luego hizo la maestría acá y el doctorado lo concluyó en medio de la pandemia, todo por Zoom en el año 2021, trabajando más o menos en este mismo tema sobre la estructura de la Vía Láctea derivada de la observación de fotometría. Luego estuvo un año postdoctorado en Illinois, trabajando con Gaia. Luego, estos 2 últimos años, ha estado en España, en el Centro de Estudios de Física del Cosmos de Aragón. Y los próximos 2 años va a estar en el Instituto de Astrofísica de Andalucía, en Granada. Bienvenido, Jairo, a ver qué has hecho estos últimos años.
Okay, I'm going to show you the work that we have been done in the last 1.5 years that I have been working in CEFCA in collaboration with Andrés del Pino Molina and Carlos López San Juan on the J+ collaboration. And when I started to work there, the team told me that, okay, J+ was originally thought for research on extragalactic astronomy, basically high redshift galaxies and many other topics also in the local universe. But J+ was conceived as the little brother of a larger survey, which is the J+ survey. But at this point, they told me, okay, we are observing galaxies, but J+ is also observing stars. So what about if we got the photometry from these stars, and let's see if we can recover some information from the star-formation history, particularly on the Milky Way disk. So let's start with this very nice picture from the Gaia people. When you can observe here the density of stars within the galactic plane, obscured by the annoying dust, which is always a problem in this kind of analysis, because this is always affecting the photometry and biasing our results. And we try to do our best, taking different or testing different 3D extinction maps that are available in literature. And you can observe here, you cannot observe it here, but we have 2 different populations in this plane. Some people call it the thick disk, which is a more high population with respect to the galactic plane, and the thin disk. And we know from spectroscopic surveys that the galactic disk can be split in 2 different populations in this plane. In the horizontal axis, you have the iron anodas, and the vertical axis, you have the magnesium anodas. And you can observe these 2 different populations, call it the low alpha population in the thin disk, in the galactic disk, and the high alpha population. And this is a very hot topic in the history of the Milky Way, because there are a lot of discussion about what is the origin of this bimodality in this. And there are many discussions about this, but I brought a few for you here. For example, one of the most popular of them, for example, the 2-infant model when along the galactic evolution. On stars near to the galactic plane that is moving in both sense, outward and inward, the disk always near the galactic plane, or mergers, large mergers. We know that the Milky Way is not alone in the space. There are many galaxies orbiting around them, and some of those galaxies are near enough to be merged to the Milky Way system, and this process always affects the evolution of the Milky Way depending on the mass of the satellite galaxy, but also can affect secular process within the galactic, within the Milky Way. For example, the star formation history of the Milky Way. So, but also, and these kind of mergers can produce the necessary conditions to produce this kind of environment. But also feedback is also enough to produce this modality. So there are many mechanisms that can produce this kind of description. But from spectroscopic surveys, we can also have the positions taken to Gaia. Sorry, the spectroscopic surveys in combination with astrometric surveys like Gaia can derive the age of these stars. Because if you know the position, you can get the absolute magnitude, for example, and through fitting in the HR diagram, you can derive an age for these stars. And the nice thing here is that you already know the metallicity because you got a relative value from spectroscopic surveys. So you are not worried about age metallicity degeneracy. So you can get reliable age estimations, and in that way you can produce this kind of plots when you can observe how the age is distributed along the same space. Metallicity, the iron abundance and magnesium abundance, but also how they are distributed according to the position of the galaxy. In these titles, you can see different beams of radial galactic, the radius with respect to the galactic center, where the sun will be around this interval. And you can also observe different beams on absolute position of an absolute in the absolute value of the vertical position for 3 different beams. 0 and 500 parsecs up to 1 kiloparsec, and from 1 kiloparsec to 2 kiloparsecs. And you can observe how this plane that we have been observing is changing along the different positions of the galaxy. And for example, you can observe how in the inner part of the Milky Way disk, we have mainly populations on the alpha enriched section of this plane. But also you can observe a kind of evolution on this chemical evolution of this inner part of the galaxy. And if you go to the external parts of the disk, you can observe how this alpha enhanced and old population is disappearing. So it means that, for example, we used to link this population to the thick disk, and that we are assuming that the thick disk is more concentrated than for example, the thin disk, which is associated to this population with this low alpha, which is a low alpha population, and around the sun, but describing larger dispersion on iron abundances. So there is we can get a lot of information from these kind of planes, but I do not want to go deep in this discussion, maybe for questions or for the after session. But yes, I would like to go to this more interesting for me diagrams. For example, satellite collaborators, they get radial velocities and proper motion for Gaia, and the metallicities from the spectroscope from I forgot it, Gala. And sorry, spam. And they define 4 groups in this space that you are observing here: iron avalanches and tangential velocity of the stars. And they define these 4 groups. And okay, you know the metallicity and alpha enhanced and alpha avalanche, so you can fit in a pretty variable way the age of each star. And then you can build this age metallicity distribution for each group, as you can see here. Group A, B, C, D, A, B, C. You have in the horizontal axis the age, and the vertical axis you have the metallicity. This is a notation for metallicity from models, for example, from isochrones. And the probability distribution is in color. So the redder, the more, the larger the probability to find a star in this region. And you can observe here very interesting things. Let's go from low rotational to high rotation. When you are observing the population D, you are observing that this is a pretty old population with a very old metallicity. But you also are observing a pretty old, very metal poor component in this population. This population is likely to belong to the stellar field. But the population C is more interesting for the topic of the Milky Way disk, because we are observing the population D, which is a bit more rotational than the population C. Population D has a very narrow metallicity evolution, metallicity enrichment, as you can observe here. And it took place between 13 gigayears ago and 8 gigayears ago. And you have residual contributions at intermediate and younger ages. But if you go to population B, which is thin disk, it is likely to belong to the thin disk, but it has a large dispersion on vertical velocity, so it is a bit thicker than the younger thin disk. And you can observe that there are a very young star formation episode, or very young now, intermediate age star formation around 3 gigayears ago. But if you go to the population A, you can observe also 2 different episodes of star formation. And one very interesting one is this one that is near to 6 gigayears ago, which has the same place in time of the Sagittarius pericentric passage.
Jairo,
So, yeah.
Is that rotational velocity or radial velocity?
It's tangential.
Tangential.
Yeah, in cylindrical coordinates centered on the galactic center, the velocity that is the product between the angular velocity and the radius. That's it. It's rotation. It's rotation. Yes. So,
Does that make sense? I mean, because if you have an event of star formation because something hit the Milky Way, I will expect strong radial velocities, not strong tangential velocities.
I know, but I don't know if I have a link to the. I mean, maybe the star formation is triggered by the merger, but I don't know how it is affecting the kinematic of the stars. I'm not sure of that for the moment. Yeah, and the last result that I want to show you in this spectroscopic section is that this very nice result from Shannon from 2022, when they got data from LAMOST, and they perform a hard constraint on the stars, and they select the early phase sample, which is a high alpha a selection from the Lamos catalog and stars with a low angular momentum, which is, and with this selection, they were targeting pick these stars. And they know the effective temperature from the survey, and they made a cross match with, I think, Dumas, and with the parallax from Gaia, they built the HR diagram, and they fit the age of the stars in this section in the subgiant star phase, where the ages are more reliable. And you have a very low uncertainties of age inferences here. So, and they build this age metallicity distribution, age in the horizontal and island on the vertical. And you can observe again this narrow chemical enhancement on enrichment on the metallicity of the stars, and starting in around 12 and 13 gigayears ago, and it has and it stopped around 8 gigayears ago. So there is a very marked interval similar to what we observe here. So, but what happens if we do not have photometry spectroscopy? We also have photometry, and in this case, photometry has some advantages over the spectroscopy. For example, if you want to study the star formation history of a given population, you want to have a good level of completeness on your sample. The spectroscopic surveys are limited to the input catalog, so it is not have they don't have a uniform covering of the sky, and they are also limited to a few stellar spectral class. I mean, for example, they only are targeting two-knob stars, subgiant stars, or giant stars. So the incompleteness level in the spectroscopic surveys are poorer than the completeness on photometry. That photometry have a better uniform covering on the sky, and they are only limited by the limited magnitude of the telescope. So you can if you have several filters, you can build the color magnitude diagrams, and from these ones you can get also ages. However, there is a problem here. In the previous case, in the spectroscopic case, you observe that we are not worried about the age metallicity, but here we are suffering of that problem. And we must be careful when we are fitting ages here, because two different isochrones, as I will show you later, two different stars with different chemical abundances, they can look similar in age. So that is a very, they can look similar in the color diagram, but they are very different on age. So I'm going to explain this later. So from these color diagrams, we can also recover the star formation history, as we have been done here in IRyA with Gustavo and Daniel Diaz. And we have recovered in the solar neighborhood the star formation history in 2 dimensions, in age and metallicity dimensions. And you can observe here the marginal distribution of this 2-dimensional distribution. Basically, you are integrating over metallicity and get this map, and if you integrate over age, you get this map. So this one is the metallicity distribution, this is the age distribution, and this is the age metallicity distribution. But because we took into account to correct or to work with a complete sample, we can recover from this the star formation history. But the important thing here that we found different peak of star formation histories and the increasing star formation history for ages between 4 and 0.5 gigayears. One of the interesting things here that we found is a peak of star formation between 4 and 6 gigayears ago, similar to that we observed in the preview in the H metallicity distribution from Galactic. And this, we also found this chemical enrichment on the population. So Galactic and collaborators also analyze the solar neighborhood, but with a more sophisticated model. They are fitting also the color magnitude diagram, and they recover these very nice results. And the difference between this panel, in the left panel, in the right panel, is the models. In the left panel, they used parsec models, and in the right one, they used Basti models. And they recover a very unexpected decreasing H metallicity relation, and after 6 gigayears, the chemical enrichment start. You can observe here a kind of jump, and then they found this chemical enrichment, which is more expected for the nearer part, the inner parts of the thin list, the inner parts of the thin list. I forgot how can I say. Clumpy star formation history is due to the low number of stars, because you can think that maybe these are different star formation episodes, but in a smaller volume like the solar neighborhood, we have a low number of stars, so we have a high. This result is affected by higher statistical fluctuations in this path, so it is not necessarily a star formation enhancement in this part of the star formation history. Riesler and collaborators also analyzing the Gaia color magnitude diagram, they found that they analyzed, but they go farther from the solar neighborhood, and they analyzed a sample within 2 kiloparsecs, and they found this very interesting result. They found that the star formation is decreasing within this 2 kiloparsec sphere, and suddenly they found these peaks of star formation. But they find not only one, they found 3 of these star formation peaks. After they compiled many information about the Sagittarius galaxy orbits from different works, and they tried to find what are the predicted pericentric passages from those observations, and they found that many times on this orbital analysis, the pericentric is the first pericentric of the the first pericentric passage of Sagittarius with the Milky Way is around 5 gigayears, which is in agreement with this peak of star formation. But also, these 2 additional peaks of star formation are also in agreement with the second and the third passage of at least with the second passage of the Sagittarius galaxy.
Right. So the inset is the current star formation. The small. The inset, the small graph.
It's a zoom. Yeah.
On the most recent ages.
Yeah.
So it's basically what's happening now in the rightmost part.
Yeah.
So we are in a peak of star formation.
Here.
Yes.
Yeah. Yes, that's true. There is another peak here, but I don't remember pretty well if they discussed if this peak is. But yeah, it looks like there is a pericentric passage here also. But yes, I don't remember that part of this. So that was the thing that I said previously, that this merging process can affect the star formation history or the star formation rate on the Milky Way disk. This is a similar work, but now it's a combination between photometry and spectroscopy, because the authors here, Fernandez Albarde and collaborators, they separate the thin and thick disk kinematically. And they define a sample for the thick disk, which is and for the thick disk, the result for the thick disk in the left panel. Again, horizontal axis is the age, and the vertical one is the metallicity. And you can observe the split in age in this result. And how can observe you also how the thin disk has a very complex, in comparison to the thick disk, very complex star-formation history. But also you are observing again this negative evolution, this negative or this depletion on chemical elements as function of age here, similar to what found Galactic in the solar neighborhood.
Jairo, sorry, I misunderstood something. What's the difference between the plot that has M over H and the plot that has Z over H? This has Z over H, and the other one has M over H.
I think it's the same.
Okay.
Maybe the author has
Okay.
different.
Different authors, so it's meta.
Yeah,
Jairo,
they are the same thing, but I don't know
Okay.
why they put set. But it's symmetrism.
It's different papers.
Jairo, what's this diagonal on the right hand side?
This one?
Uh-huh.
I don't know. Maybe it could be some star from the halo. Maybe the selection, the kinematical selection is not perfect, and they are getting some stars.
Línea tan pura, medio.
Yeah. Javier, maybe they are using different ones because in this case they use only solar scale isotones, and because they are taking advantage for I think it's from Apogee or Lamos, I don't remember very well. They can recover the true metallicity because they have the iron abundance and the alpha enhanced abundance for each star, so they can compute the total metallicity of the stars. Maybe that could be the reason for different notation. Now let's talk quickly about J+. This is the Observatorio Astrofísico de Havelambre, and this is the telescope. It's 80 centimeters diameter mirror in this telescope, and there is a camera here with the set of 12 filters. And those filters are configured in this way. There are 5 wide filters, which is similar to the those one in the S1 Digital Sky Survey, the G, R, I, and Z, and there is an additional one, which is the U, and you can observe here the corresponding central wavelengths and the full width at half maximum. And there are an addition, and these broad filters are designed to feed, for example, or to study the pseudo-continuum of any of the photospectrum. And the narrow bands, as you can see here, they are 7, and they are targeting particular spectral features which are useful depending on the size scales to study the photospectra. And you can observe here 3 examples for 3 stars, an A0 star, and G2 star, and K3 star. And you can observe in gray the spectrum of each star and how the photospectra measured by the J+ survey, by the J+ telescope in different colors. You can observe here 3 different cases and how the spectral features of each star can give us information about, for example, the age of the star and some chemical features of the star. This is in the work that we have submitted a few days ago. We analyzed the J+ DR3 published in Lopez and Juan in the last year, and this is the sky coverage of this data release. You can observe here the different limiting magnitudes of each filter band, and you can observe the sky coverage. And for this limiting magnitude, you have more or less 30 million objects. So from these objects, we select only stars, and for that we use the Banjos classifier. I'm going to comment briefly posthumously this Banjos software, and they can provide me the probability to accept or reject the stars. So I use it to select stellar objects. And because the pipeline of the J plus is based on the structure, I also have many output parameters, morphological and photometric parameters from the structure. So I use it to get relevant photometry. And from a completeness analysis, comparing stellar counts with the raw survey and the counts after the first two selections, we defined these two limiting magnitudes, completeness magnitudes, which ensure about 80% of the completeness of the sample. And finally, after all these selections, high and Gaia selections, also we are analyzing a star within 5 kiloparsecs. We use only the rubber to avoid the spurious parallaxes. And we got approximately 1.3 million stars. And this is an example of how the sample, these 1.3 million stars, are distributed around the disk. So this is the CND, and we have, and in this work we perform isochrone fitting. You can observe these 2 parsec isochrones, and we explore the age of this sample. And in this panel you have the chromatic diagram for narrow filters, and in the middle one you can observe the chromatic diagram for the broad filters and the distribution on vertical set.
Your points are already corrected for extinction.
Yeah.
Already corrected, but still the observed low mass stars seem to be hotter than your isochron. I mean, they are a bit off.
For this metallicity, yes.
It's a metal.
Yeah, it's for in logarithmic scale minus 0.2. Okay. But I think there are many unresolved binary stars here, so I'm pretty sure that most of these stars in the border of the main sequence, they are not going to be fit by the richest isotopes. But yes, that is a problem that we deal with. We still don't deal. So yeah, we developed this methodology to fit the CND diagram in the 12 filters of J plus, and we took advantage on this section of the J plus in the chromatic diagram. As you can observe in different green tones, you can observe the age, and you can observe here how the age is very correlated with the color and magnitude of the isochrons in this region. But something interesting also, you can see here in the bottom panels, when you can see in different orange tones the metallicity, how the metallicity in this low mass region of the main sequence is independent of the age. So in this case, you are not suffering age or metallicity degeneracy here. So this is a nice region to explore the metallicity of the population, and we did it because we don't care about the age here. We can define a prior metallicity using this region, because the degeneracy, as I commented previously, is always present here, because if you put different metallicities for the same ages, you can get this overlapping between different particles. These are only 3 ages and 3 metallicities. So imagine this problem with many ages and many metallicities. So then, sorry, this is not good. This is the isochrons from Basti models that we used. Here, this particular plot, I bring it here because we have sensitivity to alpha elements. You can observe here, we took here 2 isochrones with the same metallicity here, and for the same stellar phase in the turn-off main sequence rays. And we compute the difference in magnitude for solar scale isochrones and alpha enhanced isochrones. And we compute each filter for this difference for each filter. And we observe that the largest difference between the solar scale and the alpha enhanced case is in the blue filters. So for the 3 different ages, you can observe here how the old ages, which is the dashed dot line, has the largest difference. So this is very important for our analysis because that means that we can, for example, be sensitive to detect these populations because the thick is alpha enhanced and is old. So this was a promising signal that for this work. And this is the result. So we took the color harmonic diagram with the 12 filters and we fit isochrones that was more than 1,000 isochrones with a range of metallicities. As you can see here, each bin is for metallicity and each bin is for age. And you have the age metallicity panel here, but this is the star formation history of the sample that I showed you previously. And we can observe, for example, that we separate in the isochron fitting 2 groups, the alpha enhanced group and the solar scale group. And you can observe here this trend, this chemical enrichment, this trend that is showing us, or this footprint of this distribution, when we can observe a metallicity enrichment here. It is not narrow like in the spectroscopic case, but we are observing a chemical enrichment here. And we are observing a concentration of all ages for the alpha enhanced isochrones. And therefore, for the solar scale isochrones, we are observing that these isochrones are contributing mainly young stars, and there are, and it is showing us another chemical enrichment from 10 gigayears up to intermediate age. We don't have young ages because the level of incompleteness on our sample, because we have a problem with CCD saturation, so the brightest stars are saturated and our completeness limits reject those stars, so we lose a lot of information from young stars. So that is the reason that we are using young stars here. And okay, if we have an age metallicity distribution for these stars from this previous result, we can go back and okay, let's define a probability of a star to have a given age and metallicity. Okay, we did it, and we found that if we plot these individual age metallicities and ages on the galactocentric coordinates, you can observe metallicity trends. So here in the horizontal axis, you are observing the x coordinate or x galactocentric coordinates, and in the vertical axis you have the z galactocentric coordinate. It is the height with the galactic plane. In color, you are observing the metallicity, and you can observe the sun position here in this little dot, and you can observe how the high metallicities are more concentrated around the galactic plane. Now, if you do the same, splitting in different age bins from the youngest to the older here, this way, you can observe how the metallicity is also changing. For the youngest panels, from the younger panels, you can observe how you have more contributions on high metallicities, and they are concentrated in the galactic plane. But if you go to the other ones, you observe more extended more extended metallicity distribution. And you have the metal pool contributions at this metallicity. So this result is showing us that we can also extend our analysis to the stellar populations along the Milky Way, and we can also do the same in the galactic plane, and we can observe metallicity trends along the galactic disk for different age beats. So, and finally, there is an additional work that we are doing in the J+ team, and it is employing machine learning on the analysis of J+ photometry. As you saw previously, you can get a spectra from a spectroscopic service, and you have the photospectra from J+. So you can train, in this case, neural network models to associate or clustering in groups of stellar parameters, for example, metallicity, effective temperature, etc., and alpha metallicity too, and you can recover metallicity at alpha enhanced and another stellar parameters directly applying this trained neural network to J+ photometry. And you can observe here how the true value, which comes from a spectroscopic service, I think is a mix between Lamoste and apogee. And you can observe that one-to-one relation with the predicted one by the neural network. But this is a bit tricky because this is for the training sample. So in the training sample, everything is working well, but you need to apply this network to the whole J+ catalog, and you should be careful with that. So this is a work in progress, and we hope to get the metallicities with these uncertainties. But there is another works. Maybe they are not using neural networks, but they are using, for example, another clustering methods. And I did this plot, for example, to compare with the previous plot that I had shown you from the apogee survey. And from these individual ages and metallicities predicted by these neural networks or these machine learning methods, you can plot this metallicity and alpha enhanced plane as I had previously shown in the case of the spectroscopic service. And you can plot also the age because you can also perform isochron fitting here. You can observe these trends. For example, you can observe similar to the metallicity distribution on apogee, that you can observe how the population that probably belongs to the thick disk, how it's disappearing when you go to further positions, respect the galactic center, and you can observe how the thick disk has a smaller contribution on the iron and alpha distribution. And additionally, with this kind of catalogs, we can plot and cross-matching with Gaia. We can plot again the rotational velocity and the metallicity, and we can define groups similarly as done by Saho and collaborators, and check how these samples are distributed in age and metallicity, and you can observe this different distribution. Okay, this one that are likely to belong to the halo. Observe again this narrow enrichment probably for the thick disk, a more complex distribution for the thin disk. So this is an ongoing work. We are highly motivated with this methodology because we can find a middle position between a spectroscopy of high resolution and broadband photometry. So and we can with this analysis, we can find a position between these two very wide separately kind of analysis, and took the better from spectroscopic properties and from the wide band photometry analysis. So this is the summary. I can stop here. Thank you.
How are observation going? I mean, when do you expect to have the full sky survey? Well, the full sky, I mean, full sky that you can observe from your right, yes.
Okay, I'm not sure. In the case of J+, the data release 4 is coming soon, and it looks that it is more than the height of the. So I think.
Which portion was the one that you used, the PR3?
Which portion?
Yes, I mean, what percentage of the sky?
I don't remember it, but it is. I don't remember what is the exact percentage, but I think it's below the height of the total coverage.
Yeah, for the full or
No,
not full.
it's not the full yet. Yeah, the analysis that we are making with Andres Del Pino is for the maybe in November it's going to be released.
And why don't you use also the data from the other, we've taken the other telescope, the J-PASS?
J-PASS. Yeah, there is an early release for J-PASS, and I already take a look on that data. There are still some issues. I have the same problems, the same saturation problems. Actually, it's worse because it's a larger telescope, and they are taking large exposure times because they want to. They are targeting galaxies. So for the moment, I think I cannot analyze yet the J-PASS.
Kind of. Can you put the transparency 617? I think it is the one that has the isochrones. The other one, the next one. So, what is your uncertainty in the fluxes? Because I mean, my impression is that just because of the uncertainty in the distance, you have a strong uncertainty in the vertical axis, and then how reliable are your age estimations, or
Yeah.
how much you can be confident on discerning between one chemistry and the other? No?
Yeah. Yeah. In that region, the H analysis, the degeneracy, it's larger when you have larger errors. That's a fact, a very important fact. And when we define the isochrone width to feed the data, we define that the separation is going to be larger than these errors, these photometric errors. However, we found that the photometric errors are small, so we were not worried about that. The dispersion, the large dispersion or in this color diagram is mainly due to the uncertainty on parallax. So in that case, the blurring is more due to the parallax error. So we took care about that, but we also use, for avoid the H degeneracy, we use a prior mechanism because we know how is the distribution on this sample thanks to the analysis on this region of the CMB. In the paper, we present the distribution of metallicity that we infer from this low mass, low mass stars, and how it is compared to the spectroscopic ones. But yes, the analysis was enough to get about this this age uncertainty on the analysis. These are the uncertainties on age according to the photometric.
I have a question. I'm curious about why you show the number of stars in some of the plots. Why is
Why
important?
what?
The number of the stars.
In which slides?
Why is important the number of stars in the plots, for example, of
The plots that you have with yes,
those, for example. Why is important to show the number of stars?
It is important because, sorry, I forgot to comment, but these distributions are pixels. And we are counting the number of stars in each pixel, and we are taking the average on each pixel. And these values of mean metallicity are going to be meaningful when the number of stars is large. So I plotted to show to the reader that, okay, we have here these numbers of stars, so don't forget that these stars are distributed here, and the count on each pixel depends on the number of stars. The standard deviation on each pixel is going to depend on the number of stars. In the appendix of the paper, we show the standard deviation for each pixel. So that is the reason that we need to know the number of stars in these panels.
Neural networks plot. You have two panels.
This one?
And the brief.
This one?
No. You have another one. You have the training set and the alpha has this one.
Sorry?
That you have in the alpha true seems to be larger than the alpha
Predicted?
You have another plot like this?
No, this one was private communication with Andres Del Pino. But yeah, I thought there is a good agreement here. But yes, this is a more difficult chemical abundance to derive. But yeah, they are getting this dispersion problem. Yes. But it could be worse depending on the photometric errors and biases, etc.
They predicted this by an interpolation, or how they manage it? Because
Normally, they train the neural network, and there is a lot of things there that for the moment
usually the stars are either 0 or conform. It's not discontinuous, right?
Yeah, but they are making groups, and they have many continuous values from spectroscopy. So they are not making. They are not fitting a spectral model, stellar evolution models. This is more almost semi-empirical.
That's guessing. Any other question?
No,
Nothing. Some questions? Okay, thanks.
¿Alguien que haya faltado de entrarse al láser? Sí, vale.